Hi everyone, I'm Lorenzo Contento from the DeepPumas team at Pumas AI. So today's the second webinar in a new webinar series about DeepPumas. And today I will talk about using generative machine learning to enhance simulation accuracy by essentially learning the true random effects distribution in the training population. So okay, so I will start with an overview of the methodology and the results, a bit more from an intuitive point of view, and then I will go to some slight theoretical results, and then I will show you a hands-on example with some code. So we are interested in the random effects distributions. So random effects are essentially the power of nonlinear mixed effect modeling because they allow to take into account the inter-subject variability. And however, this requires the modeler to make some assumptions on this variability. So usually what people do is just say, we assume that the random effects are distributed normally or log normally if they must be positive, and maybe we can put some correlation between the components, but that's the usual case. If someone is really fancy, may use beta distribution or other kind of standard distributions, but all of these are pretty simple distribution from a modeling point of view. However, not all distributions that can occur in the real world are simple. So you may have some non-Gaussian distribution, for example, that are skewed, which could be modeled in a parametric way, but one a priori it's difficult to say a priori whether skewness will be necessary. Even more difficult to model with standard distributions are distributions that show nonlinear correlations between the random effects. For example, here we can see that there is a clear dependency between eta1 and eta2, so they look like a sinusoidal dependence. And if you try to approximate this with a Gaussian distribution, you will get something that will cover all of the true distribution, but will also cover some points that are outside the true distribution. So this means that using a Gaussian approximation here would lead to overestimating the variability that is present in the random effects. And another common way where the standard distribution no longer work are if there are multiple modes. And you can do something like Gaussian mixtures in this case, but that requires you to add an additional hyperparameter, the number of modes that you need to tune and learn together with the rest of the model. So we would like to find a better approach than that. So our proposal is to, before looking at what we propose, let's look at why is this important, why is this a problem. So let's start assuming for a moment that the observation model of the nonlinear mixed effect model is correctly specified. So this essentially means that for each subject, there are random effects values that fit the data for that subject very well. So this is usually the case if we have a correctly specified observation model, and to avoid problems, we will assume this for the rest. And so if we do prediction based on subjects that have plenty of data for each of them, then even if we have misspecified the random effect distribution, the effect of this misspecification will be small. In particular, we will still expect to have low bias and low uncertainty for the empirical based estimates, and also consequently for the individual predictions. And this is usually the case that holds for the training population, because training population is usually measured in a control setting in which for each subject we gather an amount of data that is sufficient to correctly and estimate the empirical base estimates for this subject. And a way to check whether this is actually true is just by using the usual fit plots, or just looking at individual predictions for each subject and seeing if we can match the observed data very well. So if this is true, then we have also in a way checked that for each subject there exists random effects that fit the data quite well. So for the training population, usually things, as I said, go well. However, when we look at subjects that have only limited amount of data, for example, partial observations, because we were only able to observe them up to a limited amount of time, or even in the worst case, only baseline observations, then in this case, we have less data, so the influence of the misspecified distribution becomes larger. So this leads to higher bias and more higher uncertainty, and every result that will depend on this prediction will be negatively affected. So, for example, to give a concrete example, personalized treatments that try to predict what dose you should give a patient after you have taken only a limited amount of measurement, this will be impacted by the misspecified distribution. And we can even assume that we have no data and try to make prediction based on no data, which by any other name, they can be called simulations. And these instead will be driven uniquely by the misspecified distribution, because we will just sample random effects from the misspecified distribution and use them to simulate new subjects. So this will have the highest and bias and uncertainty among all these cases. And again, practical results such as study design that are based on simulation will be negatively affected. So this is also easy to check whether this problem occurs, and the usual approach is to use visual predictive checks, in which we compare the training population with the synthetic populations generated by the model. So this is an example of a bad VPC. So probably most of you are familiar with this plot, but for those of you who are not, in black, we have 3 quantiles for the training population. And then we simulate, let's say, 1,000 synthetic populations. For each of these populations, compute the same quantiles, and then use those quantiles to get uncertainty intervals for each of the quantiles. And if the quantiles from the training dataset lie inside the confidence intervals, then everything is well. But if they lie outside, then there is indication that there is a discrepancy between the two distributions, the one defined by the training population and the one defined by the model with its misspecified random effects distribution. Okay, so now, for our proposal, so instead of sampling from the misspecified distribution, we propose to use a different one. So I will not give you the final answer immediately, but I will try to build towards it. So a first candidate could be sampling from the empirical base estimates for the subjects in the training population. So if you let's consider 2 random effects, and then we can plot the empirical base estimates and obtaining something like this. And instead of sampling from the misspecified distribution, we just choose randomly one of these EBs and use that to, for example, to simulate new subjects. So the advantage of this is, since we are picking EBs, which are values that are able to recreate the training subjects pretty faithfully, assuming that we had enough data for each subject, obviously. Since we can recreate the training subjects, then the training population can be recreated faithfully, and the VPC, for example, should be more in line with the training population. However, this will still lead to some problems. So while with the misspecified distribution, we may overestimate the variability of outcomes. With this approach, we will underestimate it very probably. This is due because values of the random effects that are nearby the EVEs are probably going to lead to data that will still fit the observed data very well. So this is because the EVEs is just the best value among the random effects that fits the data, but values nearby could still fit the data pretty well. So it is reasonable to conceive that all of these points that are, for example, in this cluster in the middle, they are still pretty reasonable values of random effects, and that they should be included in any random effects distribution that should be taken in consideration. So a way to take this into account is to not just use the EVEs, but to use the posterior of the random effects for each subject. So the posterior essentially takes the a priori distribution of random effects, that is our belief about the random effects before seeing any data, and updates it with the data that we have observed, generating a new corrected distribution, the posterior, that, for example, exclude values that are incompatible with the observations. So I've plotted these posteriors by using some kind of contour lines around each EVE. And so those represent the points that are compatible with the observation for that subject. So if we consider then the union of all these posteriors, we get a better candidate for the random effects distribution. So this will still recreate the training population faithfully because of the definition of posterior, and will also include novel subjects that are not present in the training data. However, there are still some problems. The first one is that the probability density function cannot be computed. And this is a requirement, for example, if we are going to do prediction based on partial data. It is not a requirement if we are just interested in simulations. And the second point is that, especially if we have a small training population, the problem of underestimating the variability is still there. So while we can generate more subjects than before, as you can see here, for example, we still have some places between the posteriors that are not covered by them, but could still be linked to plausible values of random effects. So to correct these two problems, we finally reach our proposal is use a generative model that is fitted on the posteriors and approximates them by smoothing them out. So a generative model is a machine learning model that essentially can be trained on any distribution, and it will try to approximate it. You may be familiar with all the recent advances in generative modeling, such image generation and chatbots, etc. They are at the simplest ways to sample from very complex distribution, for example, distribution of all images or distribution of natural language. So they belong to the same class of models that we are going to use here, but the models we are going to use here are much simpler, since they only need to deal with, for example, 2 random effects, so R squared, or let's say we have 10 random effects, R to the 10, so big real value spaces, but still very different from the space of natural language, which is even larger. But in the end, they are just ways to learn the distribution. So we will learn the distribution of the posteriors and then sample from it. So the interesting thing is that here we are proposing to approximate the truthing and say that using the approximation is better. And the reason why the approximation is better, well, for once, we can compute the PDF of this approximation pretty easily. And the second point this has a kind of regularization effect. So it allows us to sample a much larger number of subjects. So here we see that it covers completely this cluster. So all the subjects that were before excluded, now they are they can be generated by this distribution. So this, I said, is a regularization because, as all regularization do, they penalize the performance on the training population, which will be recreated less closely, because the best way to recreate the training population is just use the posterior. But by losing something on the training population, we may potentially gain on unseen data. So since we are not excluding similar subjects that were not, however, in the training population, we may potentially perform better if we encounter those subjects in the real world afterwards. So that are the reasons why we think an approximation is going to be better rather than the real thing. And if we indeed apply this method, and we see that, for example, the VPC is fixed so that the simulation performance is improved, and we can essentially treat populations generated by the model as very similar population to their training population. So on the left was the VPC I showed you before, and on the right, after applying this method. And you can see that, except some imperfections, that this is a real model on real world data, so some imperfections are always expected, but for most part, the VPC is fixed. Okay, so let's give some very slight theoretical justification. A full theoretical justification is still underway, but I think I can give you some intuition on why this should work, and also give you some idea on when instead it should fail. So this is a very simple nonlinear mixed effect model, well, or a very general, I would probably better say, nonlinear mixed effect model, in which we have theta, the population level parameters, eta, the individual level parameters, aka the random effects, and some observations y. So this is expressed by giving the distribution of the random effects, eta given theta, and then the distribution of the observations given random effects and population level parameters. We will assume that this is the model that generates the data that we have. And the question is, given data generated by this model, without knowing anything about this model, we want to be able to sample from the distribution of the random effects. So this is obviously impossible, but we will try to do this in an approximate way. And first, we see another way of writing this model, and we can just, in a way, switch the hierarchy between y and theta by writing the distribution of y given the population level parameters, and then the distribution of eta given the observations and the population level parameters. So this is the posterior of the random effects given observations and population level parameters. So it is the object that I mentioned before. This is exactly the same subject, and we are just, exactly the same model, and we are just mixing things around, but without changing the distribution. So this suggests another way to sample from the true distribution of the random effects, which is following this procedure, sampling from the distribution of the observations and then sampling from the posterior. And the problem is, as I said before, we still do not know the model, so this is very difficult to do. However, by writing the problem using these two steps, we can get an idea of how to approximate each of these steps and obtain something that can actually be computed in practice. So let's first look at the first step. So instead of sampling from the distribution of the observation, a reasonable way to approximate this is sample from the empirical distribution of the observation in the training population. So we draw a subject from the training population and then choose the observations corresponding to that subject. Why is this reasonable? Well, the training population is just a finite sample from the distribution of the observations, which is this one here. And if we have a large number of subjects, we can expect these to be pretty close. In the limit, they will converge to the same distribution. And so if we have enough subjects, then this approximation should be perfectly fine. However, if the training population is small, this will not longer work. And also, it will no longer work if the populations to which we will apply our model are going to be very different from the population we train our model on. So this is an example of covariance shift. And for example, if you think about covariance, we may have a distribution of age or other characteristics of the subjects in the training population. And if we use a population for testing the model that has a very different distribution of this covariance, then we cannot expect that a learned random effects distribution to perform as well on that test data. So let's look at step 2 now. And in order to approximate this step, we will finally need a model to be fitted to this data. So this is the model that we will use. It makes a big but not that big assumption about the observational model, in the sense that we assume that the observational model is correctly specified. It is the same as in the true model. For the random effects distribution, instead, we make no assumptions, so it will probably be misspecified and will be denoted by p tilde. And since the a priori distribution is misspecified, also the posterior distribution will change, and we will denote that by p tilde of eta given observations and population level parameters. So this is the model we fit to the data, and once we have fitted this to the data, we can replace step 2 with sampling eta from the posterior of the misspecified model. And we can do this using MCMC, or if we have plenty of data, a Gaussian approximation. So why is this reasonable? So in the limit, as this number of data points per subject goes to infinity, we will observe that these distributions in general will converge to the same distribution. So as data per subject increases, the influence of the misspecified prior will become less and less. And essentially, the posterior will both converge to a Gaussian increasingly concentrated to the true value of the random effect. So if we have enough data per subject, as it usually is the case in the training population, then these two ways of sampling, step 2 will be essentially undistinguishable. However, there are cases that this is no longer true, and that is usually linked to the fact that we cannot identify the random effects of the subjects in the training population. This could be the case of practical non-identifiability, in the case we just do not have enough data to counteract the influence of the misspecified prior, or the more serious case of structural non-identifiability, in which no matter the amount of data, the influence of the prior cannot be eliminated. So essentially, we are not able to pinpoint the true value of the random effect for a given subject. However, even if we are not able to do this, we think that using this procedure will still lead to an improvement, because this posterior will still be able to exclude values of the random effects that are absolutely incompatible with the observations. So by essentially discarding these incompatible values, we will almost certainly reduce the variance of the random effects distribution. So, and this will lead to an improved simulation performance, mostly in tighter error bounds. Okay, yeah, if you have questions about any of this, as Lindsay said, you can just post them in the chat and I will answer them when I reach a good stopping point. So now I will just give you a one slide introduction to normalizing flows, and I refer you to this or to this review paper here that should also be posted in the chat, or to any review that you can find on the internet about normalizing flow for more details about how they work. So, as I said before, normalizing flows are a generative model of machine learning. So they are used to learn a distribution from a sample that was obtained using that distribution. Um, in practice, in the case of normalizing flow, they are an invertible function from Rn to Rn that satisfies these two properties. It is invertible, and we can compute its Jacobian pretty easily. And then, once we have this function, we can use it to define a random variable. And the way we do this is take z as an n-dimensional standard Gaussian and define the random variable x as the transformation of z using f. So we can do this for every function f, even if it has no inverse or it has no Jacobian, and we can still simulate easily from the resulting distribution by just sampling from z, applying f, and obtaining a sample from x. However, if we want to compute the PDF, this invertibility property and Jacobian property are important. So this is the formula that allows us to compute the PDF of x using PDF of z, which is just the usual PDF of the standard Gaussian, the Jacobian of f, and the inverse of f. So this comes from just the formula of change of variables for probability density functions. And once we have a way to compute the probability density function, tuning the parameters that define f in order to learn a distribution from a sample is pretty easy. We just maximize the probability of observing the sample according to the parameters. And this is done through the usual methods of machine learning. If we have neural networks, we also have to use probably some stochastic gradient descent and the usual toolkit of deep learning, but it is pretty standard. Okay, so I will show you some concrete example of what this means, just to make things a bit clearer, just to show that this is actually not too difficult a concept, at least in the simplest cases. So let's see how to model a bivariate Gaussian with normalizing flow. Well, we have to transform the distribution of the left in the distribution to the right. And well, we can find essentially an affine transformation, so linear multiplication by a matrix plus a vector that will map this into this by the properties of the Gaussian distribution. And we can see that this is essentially, I have plotted here a grid that is also transformed together with the probability density as a way to visualize the mapping. And we can see this is just a rotation and some stretching in one dimension, in one direction. If we have something different, like a bimodal distribution, then it becomes a bit less easy to imagine what the transform should be. But essentially, the trick for going from the standard Gaussian on the left to the bimodal distribution on the right is that we have to stretch the space nearby the mode of the standard Gaussian in order to separate the mass of the standard Gaussian into two modes here on the right. So you can see here the grid is really stretched in the middle, which means that the two modes get separated. For example, this is done by using a function that has a very steep slope around 0. And since we are stretching the space, the same probability mass will be distributed on a larger amount of space here on the right, so the probability density function will decrease, and it actually will decrease almost to zero in a way that allows us to separate the modes. And this is also linked to the formula I showed you before, because since we scale by the inverse of the Jacobian, which is the derivative here that the derivative is I, will lead to the probability density to become small, and so to have mode separation. However, when the distribution is more complex, like the nonlinear correlation distribution I showed you before, then it gets really difficult to get what the shape of F should be in order to go from here to here. And that's where a normalizing flow can be very helpful. So I've learned this normalizing flow to get this distribution I showed you before, and you see here that the grid gets deformed in a very complicated shape that a human would have a lot of difficulty to find out, but with machine learning, we can do it pretty easily. Okay, so now for a practical demonstration, I will go over the steps again just to be summarize them again. So we will draw from the posterior of the random effects. We will fit a normalizing flow to the sample thus obtained. We will replace the misspecified distribution in the model with this normalizing flow, and then use the resulting model as a way to make simulations or predictions based on partial data. Okay, let's go to the code. Too far. Okay, so this is the toy example that we will use. It has only 3 parameters. First 2 of them, typical value and covariance matrix omega, are going to be used to define the random effects distribution. And sigma instead is the noise for the observations. And the expected value of the observation is instead taken from the solution of a linear ODE. This is linear, so the solution can be written in closed form. And essentially, this is a function, this is profile that starts at eta 2 at time 0. And then as time goes to infinity, it will converge exponentially towards eta 1. And this could be either from above or from below, depending on whether eta 1 is above or below eta 2. So very simple model just to keep things simple. I'm not sure how many of you followed the previous webinar in the series or any other, or are familiar with Pumas, but this is the way we write a model in Pumas, and it's pretty similar to the mathematical formulation. So we have a parameter block where we write parameter names and the domains to which they belong. So typical value is a vector, omega is a positive semi-definite matrix, which is a covariance matrix, and sigma is just a real number bounded away from 0. Then we write the distribution of eta, just multivariate normal. We have some shorthands for eta 1 and eta 2. Then we define the ODE system here with initial conditions and ODE formulas, and then we have the distribution of the observations. So this is our model. So we also need a data set, and the synthetic data set that we will use will be generated with a model that will have the same observation part, so the same ODE and same noise part, but we'll have a different distribution of the random effects. And in particular, we will draw from a distribution that is my model, and where each mod presents a nonlinear correlation between the random effects. So this is essentially introduces all the problems that I've shown you in the first slide of my presentation. So this is points drawn from the random effects distribution that is used to generate the synthetic data set. And we can see that we have two clusters and that in each of them, we have a clear nonlinear correlations between the random effects. If we look at another way to visualize this, for example, using a pair plot, we can see also the marginal distributions of each random effect, and we can see that also there we already see some bimodality. On top of the bimodality, this is also apparent from the joint distribution of eta 1 and eta 2. This is not always the case. For example, if those clusters would be nearer to each other, one may observe a case in which there is actual bimodality in joint distribution, but no bimodality in the marginals. So these pair plots are also a useful way to visualize these distributions. We use the pair plot library from Julia. I cannot take credit for this visualization over here. Okay, so once we have the random effects, we can sample a population using them. So this is just Pumas code. I will just keep over it. But essentially what we do is determine for each subject which cluster they belong to. There is a certain probability of belonging to cluster 1 and a certain probability of belonging to cluster 2. Then depending on this cluster covariate, we choose the distribution to sample the random effects from. And once we have the random effects, we simulate observation data using the model and those random effects. So this is pretty simple, and we use it to generate a training population with 1,000 subjects, so pretty large amount of subjects, and also a rather small amount of noise, just 0.1, and also a decent amount of observation for subject 11. To visualize this population, I just plotted the trajectories. We see here the two clusters in which the behavior is drastically different. One cluster converges from above to a limit point which is below the starting point, and the other cluster behaves completely in the opposite way. Okay, so this is our training data. So let's try to fit our misspecified model on it and see what happens. So again, if you have seen previous webinar, you may be familiar with this. Otherwise, you may have a look later at the Pumas documentation. But essentially, here we fit the model on the training population, starting from the initial guess of the parameter using the Laplace approximation. So essentially, this tunes the noise parameter and the parameters determining the misspecified distribution of the random effect. We can then plot the VPC. This is the same kind of plot I showed in the presentation, and we can see that it's pretty bad. So all of the quantiles of the training population are out of the confidence intervals that were obtained by simulating the fitted model using misspecified random effects distribution. And this is clear. The reason for this is clear by comparing the misspecified random effects distribution that has been fitted with the distribution that actually generated the data. And so misspecified distribution in red and true ground truth distribution in green. And we can see that the misspecified distribution after fitting tried to cover the true data generating distribution, but by doing that also covered lots of random effects that are not present in the data. And also, since there are nonlinear correlations here, it also introduced some bias, which by combining everything result in this bad VPC over here. So next step is try to learn the posterior distribution using a normalizing flow. And in order to do that, we first need to compute the posterior distribution. And here I will show you two ways to do that. And the first one is using Markov chain Monte Carlo to sample from the posterior of each subject, given its observations and the fitted values that we have obtained previously. Fitted values for the population level parameters that we have obtained just above. So MCMC is, let's say, the best method because it approximates quite well the true posterior, but can take a lot of time. For this simple case, it just takes 30 seconds for 1,000 subjects, but in real-world cases, it may take much longer. So once we have sampled the posterior, we can use the same tools from Pumas to check, for example, the trace in order to check convergence, which is always a good thing to do when dealing with MCMC. And once we are satisfied that MCMC resulted in a good posterior, we can try and use it to improve the random effects distribution. And here we will first try to compare it directly with the ground truth to see that indeed the posterior is a good approximation of the ground truth. In general, obviously, this is not possible because the ground truth is not available, but this is just to demonstrate that the method works, and in the real world, you will just have to trust your posterior. So again, write the misspecified random effects distribution, in green, the ground truth, and I've added in blue the random effect posterior. So you see that it covers the true generating distribution pretty well. In this case, since we have many subjects, even trying to approximate the random effects distribution using the empirical base estimates, which are the dots plotted here, would probably result in a good approximation, because you can see they cover very well the green distribution since they are so many. But in general, when we have less subjects, these points will be less sparse and the posterior will approximate the true distribution much better. So we can also use the pair plot, and there are utilities functions in DeepPumas that allow you to do essentially the same plot as above, less pretty because plot above required many more lines of code, but this plot still allows you to compare two distribution pretty easily with just a few lines of code. So there is an alternative to Markov chain Monte Carlo, and that is using the Laplace approximation, the same approximation that is used, for example, for fitting the model. This assumes that you have enough data for each subject such that the posterior is approximately Gaussian. And this is really fast, even for very complex models, this is really fast. Can be done in very similar syntax as for MCMC, but it requires no other options controlling the MCMC method. And if we try to compare them, so the results obtained through MCMC and the result using the Laplace approximation, you can see that they match very well, at least in this case. If you have less data per subject, there will be probably a stronger discrepancy. But since MCMC takes a lot of time, and since we are going to approximate the posterior anyway using normalizing flow, using the approximation through the plus formula is a very reasonable alternative in many real-world scenarios. Okay, we have a posterior now. We have checked that it is actually a good approximation to the ground truth, and so we now just need to fit a normalizing flow to it. We essentially do this in two steps. First, we need to define the architecture of the normalizing flow. Essentially, this defines how complex the normalizing flow is. So the more complex the normalizing flow, the more distributions it will be able to approximate, but obviously computational time will increase. So again, this is not really important to understand right now. If you look at the review I sent you before, you will see that well, there is a kind of normalizing flow called coupling flow, which is the one that we use, which consists essentially in a series of affine transformations controlled by a neural network that are stuck on top of each other. And so they grow in complexity as we add more layers. So the number of couplings that are stuck on top of each other is this n couplings here. And then for each of these couplings, there's a neural network that computes the stretching factor, and the number of layers, so the complexity of that neural network is controlled by this parameter. So by fine-tuning this, you can find a good trade-off usually between fitting time and performance in terms of how well the target distribution was fit. So once we have defined the architecture, we can fit it. So we fit the architecture, which is DF as defined above, to the approximated random effects distribution. And then we can specify other options, the most important of which is the number of iterations. And this is pretty fast, only takes 2.5 minutes for this simple model. Larger models may take longer, obviously. Once we have the parameters of the normalizing flow, then we can pack them in this object, which is an actual distribution we can sample from using the usual Julia syntax for distributions. And the results are the following. So red and blue have the same meaning as before. So misspecified prior and posterior. And on black, we have plotted the normalizing flow approximation. You can see it matches the posterior pretty well. Not exactly, because normalizing flow is just a model. But as I said in the slides, the fact that it is approximated is actually a feature of this method. Once we have the normalizing flow, we can rewrite the model and plug the normalizing flow in the place where before we had the multivariate normal distribution. So this is exactly the same model here, and here instead of multivariate normal, we have the new distribution that has been fitted to the training population. This also means that we can drop typical value and omega, since they were used here, but now the misspecified prior is gone, so typical value and omega can also disappear. We can also do this automatically. If you have a complex model and you don't want to rewrite it, we have a convenience function for it, which essentially you give the probability distribution fitted through the normalizing flow. You give a new name for the random effect that is going to be defined by this distribution, and tell DeepPumas which parameters to remove, and then you are done. You get exactly the same result as the unwritten model above. And you can also do fancier stuff, like, not in this case, but if you have a model with many random effects and you only want to substitute the distribution of some random effects, you can just select some of them and tell DeepPumas to replace it with the new random effects eta. And we can also do all the steps above, so computing the posterior, defining normalizing flow family, and training normalizing flow. We can also do it with the same function. We just need to pass the keyword arguments that were used before, or just be happy with the defaults if you want, and then you can do all of the above with one line. Okay, so finally, once you have the new model, we can, for example, fit it again. This is some kind of fine-tuning. You can fine-tune the parameters that are left in order to try to improve the log likelihood. This is usually not necessary. It is definitely not necessary for small models, and maybe more necessary for larger models. And once you have fitted it, you can compute the VPC again, and you can see here that now the distribution generated by the model is completely in accordance to the distribution present in the training population. And so the VPC is fixed, and we have done what we have set up to do. And final plot, I will show also how performance on partial data is improved. So we will now assume that we look at new subjects not present in the training data. And for these subjects, we only have one or two observations. And given those observations, we want to try and predict the future behavior of that subject. So this is, for example, the case of personalized medicine, or also, for example, in oncology, it allows us to, if you have a tumor growth model, it would allow you to predict the future trajectory of tumor growth size given the first observations. So essentially, the way to do this is sample from the posterior again of the random effects given the partial observations. And again, since we have few data points, the posterior is going to be influenced very strongly by the prior. And so if you have a better prior, such as the one obtained by the normalizing flow, you will also get better predictions. And we can see this here. So in black is the actual trajectory for a new subject that was not present in the training set. And we assume that we only observe the baseline observation, so only the initial value. So in a way, we only observe eta2, one random effect. And we see that the original model, misspecified one in blue, gives a biased prediction given by the median here and a large uncertainty around it. While if you look at the prediction given by the normalizing flow model, we see that the median is essentially very near to the actual observations, and the uncertainty is much smaller. This essentially in this very simple case is because given eta2, the distribution learned by the normalizing flow allows you to, given, for example, eta2 allows you to predict the value of eta1 very clearly, because it knows what essentially the relationship, the nonlinear relationship between the two is. So by knowing that relationship, it allows you to get much better predictions. Okay, going back to the slides, just one outlook slide. So what I've shown you today is not yet in DeepPumas, but it will be available. Everything I showed you today is an experimental feature in the next version of DeepPumas. Well, fingers crossed, obviously. And we expect to have other enhancements coming during this year. And these are the two main we are working on. So first, training normalizing flow jointly with the model. So instead of doing this as a post-processing step, training everything in one goal. And the second enhancement we are working on is conditional normalizing flow that uses covariates essentially to personalize the random effects distribution for each subject. So in a way, this learns a mapping between covariates and random effects. And these mappings also is not a one-to-one, one covariate value, one random effect value, but maps one covariate value to a distribution of possible random effects values. So this, in the case a one-to-one mapping is not possible, this should better learn the actual uncertainty, the actual variability that is present in the training population. And this also allows better predictions probably based on partial data, because not just the baseline, for example, we can use to improve the prior, but also the covariates, and also allows, for example, to deal better with covariate shift, because if our data set has different, in the testing phase, has different covariates, the normalizing flow can take it into account to predict a better random effects prior for that new test data set. And with this, I've reached the end. Yeah, there are a couple of minutes left. I did not see any question on the chat. So if you have one, this is the last time to try and ask it. If not, I guess, yeah, we can conclude this here. Thank you for joining. And there's a question. How can we ensure that there is no overfitting? Yes. As usual, there is always going to be some overfitting unless you take into account regularization. So the overfitting part essentially comes from, from the fact that the training population is just a finite sample of the universe population, and so it cannot be really used as a stand-in for the universe. So this is overfitting is a case of the first first approximation step failing. So this is also what I was talking about here, that by concentrating just of the posteriors of the training population, we may exclude nearby values that may be present in the test population. And so by concentrating on the posterior, we are going to increase the overfitting. So the way we think of dealing with this is using the normalizing flow that already introduces some smoothing, so some regularization. So a way to deal with overfitting and improve performance on unseen data. And on top of this, you can also add other forms of regularization. So for example, let me go back to the code. It is going to be very quick, but just to give you an idea. So you know that there is the concept of early stopping, where if you go along the training axis, increase the training epoch, the training set will always perform better, but if you have a validation set, it will start to perform worse because of overfitting after a certain point. So the idea is that we can also stop the training early here. And since at the beginning of the training process, normalizing flow is still in black here, but it's kind of a blob, which is almost Gaussian. And only when we go through the training, we are overfitting it to the posterior. By stopping early, we can stop at a point something like this, for example, where we may have less overfitting because we are still far from overfitting, and so in a way where in a position where we may better fit unseen subjects. And the second point, covariates. So this was also something mentioned in the final slide about the conditional normalizing flow. And covariates are definitely useful. And using covariates, essentially, we think we may personalize the distribution for each subject by taking that into account, for example, having a different mean or a different standard deviation for each subject based on its covariance. And again, you may need many subjects in order to do this without overfitting, but that's life for all covariate modeling, I guess. I hope on another question. What real life data I hope, yeah, I think you can all see the question, so I will not read it out loud. So this is a pretty philosophical question. So how can you distinguish whether your model is wrong because of misspecified observational part or misspecified random effects distribution? I think the answer is, well, at least the answer I would give is not a definite answer because, as I said, it could be a bit philosophical, but if your model is fitting well the training data set when you optimize the random effects, it makes sense to believe that you have nailed the observation model. So if you can find random effects that fit the trajectories, then yeah, the models seem to be working. It's just, and then you get a bad VPC, then you say, yeah, I can fit by choosing good random effects value, I can fit the data, but I do not get a good distribution of responses. So I guess the observational model is right, and I guess the random effects distribution is incorrect. I guess this is not always the case, but yeah, when we use a model, we have to make assumptions whether we have to make the assumption that it is the correct model in a way, or at least the generative part, we have to assume that is the correct one. And if you have competing models, then you should just do model selection, compare them, and see which of those performs better. But as long as your model can fit, at least the individual prediction of the model can fit the training data set, I would not worry about that part. But it's definitely an interesting question, and I confess I've not thought about it that deeply. If there is any other question, otherwise we stop here. We already a bit over time, and thanks for joining then, and I hope this piqued your interest. And yeah, when we have a release, we will also publish some additional learning material. We are also writing a paper on this, so stay tuned for more developments on this side, and I hope you will also join the next webinar in the series.